Good morning, students. The lecture series of operating system, I covered lots of topics. Now in this class, I'm going to cover the topic process synchronizations, which is one of the most important job of operating system. So first, what do we mean by process synchronization? So process synchronization means sharing system resources by processes in such a way that concurrent access to shared data is handled, thereby minimizing the chance of inconsistent data. Maintaining data consistency demands mechanism to ensure synchronized execution of cooperating processes. Now, if we see why we need process synchronization. Process synchronization needs to be implemented to prevent data inconsistency among processes, process deadlocks, and prevent race conditions, which are when two or more operations are executed at the same time, not scheduled in proper sequence, and not exited in critical section correctly. So, on the basis of synchronizations, processes are categorized as one of following two types: independent process. Execution of one process does not affect the execution of other process. Cooperative process. Execution of one process affect the execution of other process. So if the process synchronization chapter we see, then there are lots of small sub topic: the critical section problem, Peterson solution, synchronization hardware, mutex, locks, semaphores, classical problem of synchronizations, monitors, synchronization example, alternative approach, etc. Now, what is the objective of this process synchronization? To present the concept of process synchronizations, to introduce the critical section problem, lots of objective of this topic. Now, if we see the breakdown, process can execute concurrently. So processes may execute concurrently, may be interrupted at any time, partially completed executions. So concurrent access to shared data may result in data inconsistency. So maintaining data consistency requires mechanism to ensure the orderly execution of cooperating processes. So if we see the example, suppose that we wanted to provide a solution to consumer producer problem which fills all the buffers. We can do so by having an integer counter that keeps track of the number of full buffers. Initially, counter is set to 0 and it is incremented by producer after it produces a new buffer, and decremented by consumer after it consumes a buffer. So if we see the coding for producer, while true, produce an item in the next produce, while counter equal to buffer size. So next produce is in buffer and buffer size is incremented and counter is incremented. That means when producer produce, then buffer size is incremented as well as counter is incremented. But in case of consumer, while initially counter equal to 0. So if consumer consumes, then counter is actually decremented. So in this way we see producer and consumer problem. So race conditions. So counter plus plus could be implemented as register 1 equal to counter, register 1 equal to register plus 1, and counter equal to register 1. So counter decrement could be implemented at, so register 2 counter register 2, register 2 minus decremented and counter register 2. So in this way we have C in the rest conditions. So consider execution of interleave counter 5 initially. So SO producer executes register equal to counter, so register 1 equal to 5. S1 producer execute register 1, so register 1 equal to incremented by 1, so you can produce some, then buffer is incremented by 1, so register 1 equal to 6. While consumer executes register 2, that means counter, so register 2 initially 5, so consumer executes, so then register 2 equal to register 2 minus 1, so it is decremented, that is your register 2 equal to 4. Again producer executes counter equal to register 1, so counter equal to 6, so consumer executes counter, so register equal to consumer, so counter 4. In this way we have C, the increment and decrements. Now come to another important critical section problem. So in this case, suppose we consider a system with n processes P0, P1 to Pn minus 1. Each process is critical section segment of code. So process may be sensing common variables, updating tables, writing files. So when one process in critical section, no other may be in its critical section. So critical section problem is to design protocol to solve this. So each process must ask permission to enter critical section in the empty section and may follow critical section with the exit section, then remainder section. So if we see the critical section problem, general structure of process Pi, do entry sections in critical entry section, then critical section, so exit section, then remainder section while true. So this is the structure of critical sections. Now algorithm for the process Pi, do while turn variable equal to j critical, then critical section, and turn equal to j remainder section while this is true. Now in this solution to critical section problem, so critical section problem will be solved if we consider the following criteria. So first, mutual exclusion. Mutual exclusion: if process Pi is executing in the critical section, then no other process can be executing in the critical section. So that means if any process executing in critical section, then no other process allowed to entry into the critical section problem. So it is mutually exclusive. Now number 2, progress. If no process is executing in critical section and there exists some process that wish to enter their critical section, then the selection of process that will enter critical section next cannot be postponed indefinitely. So if no process is executing in the critical section, then the progress is actually, we may create some priority to the processes so that progressively they are and try to enter into critical section problem. So bounded waiting, a bound must be exist on the number of times that other processes are allowed to enter the critical section after a process has made a request to enter its critical section and before that request is granted. Assume that each process executes at non-zero speed, so no assumption concern relates speed of n processes. So how critical section handled in operating system? To a process depending on if kernel is preemptive or non-preemptive. So we have already known in the process scheduling, preemptive scheduling and non-preemptive scheduling. Preemptive scheduling allows preemption of process when running in kernel mode, and non-preemptive runs until exits kernel mode blocks or voluntarily yields CPU. So essentially free of rest condition in kernel mode. So Peterson's solutions, good algorithm describe problem solver problem. So two process solutions here. Assume that load and store machine language instruction are atomic, that is cannot be interrupted. So the two process share two variables, integer turn and boolean flags too. The variable turn indicate whose turn is it to enter critical section. The flag arrays is to indicate if a process is ready to enter critical section. So flag I equal to true implies that pi is ready. Then do flag I true and turn j, while flag j and turn equal to j. Then critical sections, process in critical section. If flag I equal to false, then remainder sections while true. This is the solution of the critical section problem. So Peterson's solutions provable that three critical section requirements are met. Mutual exclusion is preserved. So pi enter critical section only if flag j equal to false or turn equal to I. Progress requirement is satisfied and bounded waiting is met. That is why Peterson's solution give the solution of critical section problem. Now synchronization hardware. So many systems provide hardware support for implementing the critical section code. All solutions below based on ideal locking. So protecting critical region via locks. Uniprocessors could disable interrupts. So currently running code would be executed without preemption. Generally too inefficient on multiprocessor system. Operating system using is not broadly scalable. So this is lots of problem here. Now these are some programs. We skip this. Mutex locks. So previously solution complicated and generally accessible to application problems. So operating system designable software tools to solve critical section problem. So simplest is the mutex lock. So mutually exclusive lock. So protect a critical section by first acquire a lock, then release the lock. So boolean variable indicates if lock is available or not. Calls to acquire and release must be atomic. Usually implement via hardware atomic instructions. So by the solutions require busy waiting. This lock therefore called spin lock. So this is the coding acquire and release function. So acquire while available while process is not available equal to false, then otherwise release if a variable is true in the critical section. So do acquire lock, that means critical section, and a release lock, that means the sections while true. Now another solution is Semaphore synchronization tools that provide more sophisticated ways than mutually exclusive locks for process to synchronize their activities. So Semaphore S is an integer variable, can only be accessed via two visible atomic operations, so wait and signals. So originally called P and P functions. So definition of wait operations: wait S Semaphore while S less than equal to 0. So TTL S positive with a in busy and S is decremented. And definitions of signal operation: signal S and S incremented. So Semaphore counting Semaphore integer value can range over an unrestricted domain. Binary Semaphore integer value can be range only between 0 and 1, same as mutex locks, mutually exclusive lock. So can be solved with a synchronization problem. Consider P1 and P2 that require S1 to happen before S2 created Semaphore synchronization is to 0. So P1 equal to S1, P1 in S1 signal synchronization, and then P2 wait synchronization, S2 in this way. So Semaphore implementation, we must semaphore must guarantee that no two processes can execute the wait and signal on the same semaphore at the same time. So thus the implementation become critical section problem where wait and signal could are placed in critical section. We now have busy waiting in critical section implementation. In this way, now come to deadlock and starvations. Deadlock is a mechanism two or more processes are waiting indefinitely for an event that can caused by only one of waiting processes. So this is a deadlock situation. So if we see SMQ to semaphore initialized to 1, so P0 and P1 to processes. So P0 waits S and waits Q, and P1 waits Q and waits S. Signal S, so signal Q, and signal S. These are in deadlock situations. So starvations, indefinite blocking. A process may never be removed from the semaphore queue in which it is suspended. So priority inversions, signaling problem when lower priority process holds a block needed by higher priority process. So classical problem of synchronization. Synchronization problem used to test newly proposed synchronization, bounded buffer problem, reader writer problem, then infrastructure problem. So bounded buffer problem and buffers each can hold one item semaphore mutually exclusive initialized to the payload 1 and semaphore full initialized to the payload 0 and semaphore empty initialized to the payload n. So bounded buffer problem, the structure of the producer process do produce an item in the next produced, wait empty and wait mutually exclusive at the next produced buffer, so signal mutually exclusive and signal full while true. So this is the producer process. Now consumer process do wait full যেটা full এটাকে waits mutex mutually exclusive and remove item from the buffer to the next consume, so signal mutually exclusive and signal empty, so consumer then next consume and while true. So in consumer process reader and writer problems. So a data set is shared among a number of concurrent processes. So reader only read the data set, they don't perform any updates. Writer can both read and write. So problem, allow multiple reader to read at the same time. One single writer can access and share data at the same time. So several variations of how readers and writers are considered all involve some form of priorities. So shared data learning philosophy problem. This is also another problem. Monitors high-level abstraction that provides convenient and effective mechanism for processing. Monitor is abstract data type, internal variable only accessible by code within the procedures. Only one process may active to random monitor at a time, but not powerful enough for model synchronization. This is something else. This is so these are lots of signaling this.